Do you remember from high school how they explained that, high voltage power lines have very high voltage so that they don't lose a lot of current, so not much heat is lost in them? That's not quite how that works. Also, are you aware that some people say, oh, high voltage batteries like 800 volt battery packs, they charge a lot faster than 400 volt battery packs? That's wrong. If any of this even slightly confuses you and you're like, yeah, something like that in my past, maybe I don't quite remember how it works, this video is for you. Let's jump in, and we need to draw a little electric circuit. The simplest you remember, this one. It has a simple resistance, R. Let me get my pen out. It has a simple resistor R, has a voltage, supply voltage, and of course this results in some current being drawn and flows over R. By the way, if you're from the US, you might be like, the fuck is he drawing? Yeah, see, the US draws resistors in squiggly pointy lines and inductors with squiggly round lines. And that's a bit stupid. You can't have two symbols that almost exactly look alike and expect people to see that, especially when you draw them by hand. This is not good symbol choice. Dear Americans, sorry. I'm going to use the international version, which is a resistor is a rectangle, and the inductance, they have a filled out rectangle. Much easier to distinguish. Okay, so let's get that out of the way. And this simple loop, there's Ohm's law, and that's U equals R times I. Uri, that's a place in Switzerland. I think they call it Uri, and it's a quite picturesque place. And that's how I remember it. It's a place in the world, Uri. And then there's Joule's law, is how much power is generated in that resistor, and that's U times I. I know you know that. I don't like these two equations to present them as is. They don't really show what actually they mean. So here's what they actually mean. Here's a resistor. That's a zoomed in version of the resistor we just saw. And over that resistor, there's a voltage drop. This voltage is the drop in voltage over that component. And through that component, through the resistor, there's current running through it. Now we can rewrite those two equations. That means the voltage drop over a component is equal to the resistance of that component multiplied by the current going through that component. Similarly, power. Well, what power are we talking about? Well, it's two kinds. Either it's power loss, meaning heat dissipated, or power stored in the component. And that again is the voltage drop of the component multiplied by the current going through that component. That's where most of the confusion comes from. So it's not the supply voltage, it's the voltage drop. Anyway, you're not here to see that. You're here to hear about that thing with heat and power and current and voltage. Yeah, let's get that out of the way too. So those two equations, and now you know I mean voltage drop and current going through and power loss are stored. Either you solve those two to be U square over R, to be power is U square over R, or power is I square multiplied by R. And there's a lot of confusion because people think those two are contradictory things. They are not. Not if you use the voltage drop. That's important. If you use voltage drop, those two are the exact same thing. You can heat an oven either with a lot of volts and very small amperes, so a lot of voltage and very small current, or very high current and very small voltage. It's the same thing. Yes, heat is not only current. By the way, you can solve the upper equation. If you have a desired power loss, maybe you want to heat your oven with 1,000 watts, and a certain resistance, you can solve for the voltage necessary. We'll need this later. Just to get the thing out of the way that when people say, oh, higher voltage, oh, that means better, lower current and less losses. And no, let's double power for your convenience. If you double power and use those two equations, you see you double the power loss simply by increasing the voltage by 41%. Increasing the voltage will increase the current, Both of them increase by 41%, meaning the total power then increases by 100%. Yeah, so just increasing voltage doesn't reduce power loss. It increases power loss. So there's obviously something else going on. Before I tell you what else is going on and what the true reason for the high voltage power lines is, we need to talk about cause and effect real quick. We remember URI, U equals R times I. That's the wrong way to remember this equation because it confuses cause and effect. Here you could read that as given a current, a voltage results. It's not how physics works. Math doesn't care, but physics does. And physics works like this. Given a voltage and a certain resistor value, the current results is the effect. So cause is voltage. Current never is the cause. Current always is the last in line. You can compute it earlier than that, but we'll get to this later. Now we can finally talk about the thing with the high voltage power lines, or in general, how to reduce power loss in wires leading up to wherever we want the power to be. Let's draw another circuit, but this time with two resistances. One is the load, where we want power to go, and one is the wire resistance, where we don't want power to go. But wires have a resistance, albeit a small one. We have a supply voltage, and of course there's a supply current resulting going through both of them because they're in a series connection. And both resistors have a voltage drop associated with them. So a voltage drop of UW or UL for load, W for wire. If we now write down the equations we know, first of all, the power equations, well, that's the voltage drop UW multiplied by the current, or the voltage drop in the load multiplied by the current. Then the supply voltage needs to be the sum of those two voltage drops because it needs to supply all the voltage drops. Finally, we have the Ohm's law, URI, you remember, and that applies for each of the resistors. Those are all of the equations I can think of and I need. Here, now, what do we do? First of all, look at the first two equations. And you can see that, well, the ratio of the voltage drops is equal to the ratio of the power drops. Fine, nothing spectacular. That's also equal to the ratio of the resistances from the last two equations. So that's interesting. So the power ratios is the same as the resistance ratios. Oh, wait a second. That means that the power loss in the wire is proportional to the power loss in the load, but also multiplied by the ratio of the resistances. Oh, that's interesting. Now, if I want to reduce the power loss in the wire, and I keep my power loss in the load because I want to heat my oven with 1,000 watts or charge my battery with 200 kilowatts, I have to play with the resistances. So either I reduce the resistance in the wire, making it a larger wire. Fine, you know that's true. But also increasing the resistance of the load works. And that's what we do. We increase the load resistance. Here, that's the key. So now when we increase the resistance of the load, physics decides to dump more power into the load proportionally to the power loss in the wire, which is what we want. It's a resistance change that we need if we want to reduce power loss in the wire. Yeah. Well, where does voltage come from then? Well, we only chosen a different resistor now. We've chosen to increase the resistance in our load, which automatically decreases power loss in the wire. But now if we want to compensate for that, we need to change the voltage. So we have a desired power loss in our load, charging the battery, heating your oven. And we want to minimize the power loss in the wire. That means we need to maximize the resistance of the load. Well, what supply voltage do we need then if we change the resistance of the load? Well, we can solve for that. That supply voltage is then equal to either that square root of desired power loss in the load multiplied by the resistor. You remember that equation from before? But that only is the voltage drop in the load. We also need the voltage drop in the wire, which for your convenience, I've solved that already. And this typically is very, very small. We want it small because the resistance RL is in the denominator there. Notice that we need to increase RL. Well, if we increase RL, we need to increase the supply voltage. That's where that comes from. So I need you to remember when people say that, oh, we just increase voltage, but you first changed the resistance. Because of that changed resistance, you then need higher voltage, and you change the resistance so you have lower losses. It's a change in resistance. So why fucking current? Sorry. But where does this current thing come from? Now, the problem is there's a difference between how physics works and how it's simple to calculate the result that you want. So let's look at how a student might calculate this loop. If he wants to do it quickly, he would go like, well, I will calculate the current going through the load by dividing the desired power of the load by the supply voltage. And I assume that the wire is small. Then I have current. And then I can use that current to compute the losses in the wire using that infamous I square R equation. And that works. Yeah, so that's close enough. It's not perfect, it's a shortcut, but the error is small. And I use that myself to estimate power losses in wires. The problem is threefold. Problem number one, it's not instructive. It hides changes in R, number two, and number three, it's not how physics works. So it's not instructive, meaning you use that, but you hide the fact that you need to change R. Nowhere in there does the resistance appear. That's a problem because you need to increase the resistance. That's a cause for it. That's the goal we want to do. And that's not how physics works, but it's easy to compute. So math does not care. That's important. So when you hear people saying like, oh, let's just reduce the current and then therefore we need to increase the voltage, what they probably don't even realize, all of this can only be done by a change in the resistance. Yeah, so there are people, or idiots as I call them, emotional, damn it, who think that higher voltage battery packs, like 800 volt battery packs, can be charged quicker, meaning with more power, than 400 volt battery packs. Yeah, no, that's stupid. It's just stupid. Stupid! There are consequences of higher voltage, and there are consequences in wire diameters and plugs and connectors, and I will talk about all of these in my next video that will deal with EV charging, and it will be no equations and stuff like that for everybody. Here, let's do some work, and let me show you what actually happens. Let's say I have a single cell. This single battery cell, I just assume 1 ohm resistance. I'm making up numbers here. The numbers don't matter. Let's say my charging voltage is 4 volts. You know how 400 volt battery and 800 volt, we'll get to those 4 and 8. So with 1 ohm and 4 volts, I will get 4 amperes of charging current. The result would be that this single cell charged at its specifications charges at 16 watts. Could I charge it with 100 watts? No, it would burn and die and destroy itself. So it needs to be charged like this. Well, I have 2 battery packs for you, each containing 2 of these cells. Battery pack number 1 has a parallel connection of these cells. Battery pack number 2 has a series connection of these battery cells. Okay, so what's the total resistance, the battery pack resistance of pack number 1? Well, that's half an ohm. That's half the resistance of a single battery cells because connected in parallel. In series, as you remember, resistance goes up. So the total resistance of the 2 series connected cells is 2 ohms. Cool. What's the supply voltage? Well, the supply voltage on the parallel connected battery pack needs to supply one charging current drop. So its supply voltage will be the charging current, or 4 volts. Well, what's the current going through the pack? Well, that's 2 times the current of a single cell, or you can calculate it by U divided by R. You end up with 8 amperes. Okay, so what's the charging power? Now, no matter how you compute this, you can compute it by I square R or by U square over R. It's the same thing. The result is 32 watts. Whoop-de-doo. You charge 2 cells at their specification, and 1 cell does 16 watts, so two cells do 32 watts.
Well, no fucking shit.
It's not a surprise. It's good that the physics works out and the math works out, and I hope you're satisfied with this, but we shouldn't really have to do all of these. It's just 2 cells being charged at their nominal charging specifications. Battery pack number 2. What's the supply voltage? Well, we need to supply 2 battery current drops. So that's twice the charging voltage, or 8 volts. The resulting current will be 4 amperes. And what's the power? No matter how you compute it by I square R or U square over R, the result is the same. An amazing, surprising 32 watts. Now, notice, battery pack number 2 has 8 volts, twice the voltage than battery pack number 1. This can only be done because it has 4 times the internal resistance of battery pack number 1. 4 times the internal resistance, you might be correct in thinking, well, doesn't this have consequences? Like bad consequences? To find out, I'm preparing a next video on the side to explain all of that. But for now, let's focus on they charge the same. And again, we have the truth behind everything, that there is a huge resistor change. You cannot just change how you want voltage and current. You need to change the resistance too. And this is what happens implicitly in those battery packs, which is why they don't charge any quicker or slower. So, yeah, it's sad to see people, even from the automotive industry, not understanding this. Granted, battery pack number 2 has lower current, which means the wires leading up to that battery pack can be a little bit smaller diameter. But that's not a huge change. I will talk about all of the implications of higher voltage battery packs in cars in the upcoming videos. I will talk about cables, about plugs, about internal electronics, about packaging. All of these are affected, including efficiency in the motors, but charging is not one of them. So finally, let me try to wrap all of this up. What you've seen shouldn't surprise anyone, but still it surprises many people. We're only dealing with 2 equations. 2 equations. Unless you have years of experience and your intuition is actually grounded in experience and education, you should write down the equations like I did, because I need to write them down, because my intuition about this is not good enough. If you're interested in how the mind works and why we got that wrong so easily, I can recommend Thinking Fast and Slow from Kahneman. And it explains how our brains are just not made for this stuff. Thank you for watching. If you disagree with me, write down in the comments. Subscribe for the upcoming video of the charging thing. Here's a bonus. Let me add the final puzzle piece that I've not noted in the video. You know how the high voltage power lines also have transformers? So you have a high voltage side, a transformer, and then your house. Your house has low voltage, and the transformer transforms from high voltage to low voltage. What it actually also does, it changes the resistance of the house to the high voltage side. And it changes the resistance squared by the voltage decrease. So if you decrease from 100,000 volts to 100 volts, That's a factor of 1,000. So the resistance of your house would appear to be 1,000,000 times higher than it actually is to the high voltage side. That's the magic of transformers. They work just like gearboxes, same thing there. And so that's how that finally makes sense. But that's alternating current. I didn't want to get into that. If you stayed this long, thank you for staying for the bonus. I'll see you next time. Stay safe.